In this engaging conversation, astrophysicist Neil deGrasse Tyson hosts Kim Arcand, a visualization scientist and emerging technology lead for the Chandra X-ray Telescope at the Harvard-Smithsonian Center for Astrophysics. Together, they explore the innovative ways astronomers interpret cosmic data beyond traditional imagery, with a special focus on data sonification and immersive visualization. Topics span the challenges of studying invisible wavelengths like X-rays, the unique capabilities of Chandra, the use of sound and tactile methods in representing space phenomena, and the future of astronomical visualization technologies. Kim Arcand's pioneering work in data sonification represents a transformative approach to scientific analysis and public engagement. Sonification translates astronomical data, traditionally visual, into sound, enabling researchers to hear the cosmos. This technique is particularly valuable for individuals with vision impairments, but also serves to refresh fresh perspectives for sighted scientists by engaging different sensory pathways. Beyond sound, Arcand's work extends to tactile experiences through 3D printing and vibrational feedback, offering new modalities to experience and analyze astrophysical data. This multisensory approach nurtures creativity and alternative discovery routes analogous to the accessibility benefits of urban curb cuts, improving usability for a wide range of people. Chandra's specialty lies in detecting X-ray emissions from high-energy cosmic phenomena like exploding stars, galaxy clusters, and black holes, signals invisible to the naked eye. Arcand describes Chandra as the X-ray microscope of the universe, with an exquisite angular resolution comparable to Hubble's and an ability to discern minute details in distant energetic objects. Achieving this requires unique engineering feats, such as grazing incidence mirrors designed to skim X-rays similarly to skipping stones over water. These mirrors are painstakingly polished to near-atomic smoothness, enabling Chandra to capture these elusive photons despite their relative scarcity compared to optical light. A key theme is the importance of maintaining transparency when translating raw data into images or sounds. Arcand and Tyson emphasize that astronomical images are not literal space selfies, but carefully constructed representations derived from non-visible light bands. This distinction is crucial for audience understanding, especially given common misconceptions, like those popularized by movies such as Contact, where radio waves are conflated directly with sound. The team strives to clarify these translations so the public can appreciate the process and scientific fidelity behind imagery and sonifications. Sonifying datasets can reveal subtle patterns less perceptible visually, such as rhythmic variations in X-ray data from galaxy clusters or the pressure waves produced by black holes burping into their environment. For example, the famous Perseus cluster emits sound waves at tones far below human hearing, which can be digitally shifted for audible sonification. Researchers have occasionally noted additional features through these auditory explorations that might be overlooked visually. Sonification's time-sequenced nature offers a temporal parsing of data that differs fundamentally from static images, thereby enhancing insight. Kim discusses the notable case of Eta Carinae, a massive and volatile binary star system in our galactic neighborhood, which has undergone dramatic eruptions visible in multiple wavelengths. Chandra's data reveal intense X-ray emitting hot gas forming a space croissant enveloping the system's expanding nebula. By creating detailed 3D models from observational data and offering these for digital interaction and 3D printing, scientists and the public alike can engage with complex structures tangibly, aiding both scientific analysis and accessibility for visually impaired individuals. The panel highlights the synergy among space observatories such as Hubble, Webb, Chandra, and the Event Horizon Telescope. Each observatory targets different electromagnetic bands or techniques, collectively enabling comprehensive studies of astrophysical phenomena. For instance, combining Chandra's X-ray data with Webb's infrared views and the Event Horizon Telescope's radio imaging can illuminate supermassive black holes and their feedback mechanisms regulating galaxy growth. While such coordinated observations are often planned through peer-reviewed proposals, extraordinary transient events may trigger rapid responses across multiple facilities worldwide. Virtual reality and extended reality technologies represent an exciting frontier for visualizing space data and training future astronauts. These immersive environments allow users to explore complex cosmic data spatially and interactively, facilitating deeper understanding. Kim notes that VR is already in use for astronaut training, helping simulate spacecraft operations and extravehicular activities. Popular applications like Pokemon Go demonstrate the potential of extended reality to engage broad audiences, encouraging physical activity and community building, which can inspire future scientific and educational uses. Addressing a sophisticated technical query, Kim explains the engineering trade-offs in designing X-ray telescopes. Due to the nature of high-energy photons, maximizing photon collection is prioritized over achieving purely diffraction-limited imaging. Grazing incidence optics must be highly polished and precisely aligned to capture sparse X-ray photons effectively. Engineering constraints limit how finely these observatories can focus the light, but Chandra's achievement of half an arcsecond resolution remains exceptional and sufficient for many scientific goals. Building larger telescopes with both high photon throughput and diffraction-limited performance presents formidable challenges that require ongoing innovation. The conversation reveals how sonification bridges analytic science and artistic expression. An example is given where artists have reconstructed images from sonified data, providing creative reinterpretations closely linked to the original scientific content. Instrumentation choice, be it pitch, tempo, or timbre, is a powerful parameter in sonification, with diverse sounds like saxophones, oboes, or didgeridoos welcome to represent different data aspects. This interplay enhances both intuitive understanding and engagement with complex astronomical phenomena. Kim shares details about her forthcoming book aimed at families, which explores the universe's weird and wonderful oddities in a manner that is entertaining yet informative. This project embraces the potentially unsettling or mysterious aspects of space, such as extreme exoplanet environments and ghostly phenomena, to spark curiosity without overwhelming fear. The concept of freaking out is reframed as embracing awe at the vastness, extremity, and novelty of the cosmos, making science accessible to all ages. The panel discusses how black holes do not themselves emit sound, but influence surrounding matter, producing ripples and pressure waves in hot gases that are translatable into sound. Sonifying large populations of black holes, like in the Chandra Deep Field South, produces rich soundscapes reflecting their energetic activity. Sounds may range from deep booming tones to subtle bloops reminiscent of musical compositions, enabling new ways to perceive and conceptualize these enigmatic objects. Color palettes in astrophysical imagery balance aesthetic appeal with scientific accuracy. The team often employs standardized RGB schemes to represent low, medium, and high energy bands. For example, mapping Chandra's X-rays to blues and purples, Hubble's optical to greens, and Webb's infrared to reds. However, color assignments may be altered to better communicate specific findings, as in the bullet cluster imagery, where colors were inverted to clarify the separation of dark matter from normal matter. Studies indicate that clear communication of meaning matters more to audiences than specific color aesthetics, reinforcing the priority of comprehensibility. Visualization techniques, especially 3D modeling, can reveal unexpected details in complex data sets. For instance, supernova remnants such as Cassiopeia A exhibit asymmetries and spatial distributions of elements that suggest the progenitor star turned itself inside out during its explosive demise. Such discoveries might remain hidden in raw numbers or conventional images, but emerge vividly through advanced visual analysis, highlighting the critical role of innovative visualization in driving astrophysical understanding. The concept of deep fields involves pointing telescopes at seemingly empty sky regions for extended periods to detect faint, distant objects. Chandra's Deep Field South echoes the pioneering Hubble Deep Field by uncovering thousands of previously unseen black holes and galaxies. These efforts underscore the importance of observational risk-taking and the serendipitous discoveries possible when astronomers explore the cosmos beyond immediately obvious targets. When asked if there are places in the universe where nothing is observable, both Kim and Neil agree such regions are unlikely or do not exist within current observational capabilities. Every pointing of a sufficiently sensitive telescope reveals some cosmic activity, whether star formation, black holes, or diffuse gas. New instruments continually push deeper and uncover phenomena previously hidden, illustrating the universe's complexity and the unceasing potential for discovery. The dialogue closes with enthusiasm about continued advances in technology and collaboration that will enable richer, more immersive, and more equitable experiences of the cosmos. This includes integrating auditory, tactile, and visual modalities alongside cutting-edge instrumentation, fostering both scientific breakthroughs and broader public engagement. As exploration tools grow in sophistication, so too does humanity's ability to understand and appreciate the universe's many secrets.